Can I start or no?
Yes, it's okay.
It's okay. Okay. I would like to thank the organization committee of the conference, which gave me this opportunity to speak about some of my recent results related to nucleation dynamics in supercooled barium sulfide. This work is part of my postdoc project supervised by Professor Zanotto and Professor Hino. The outline of my presentation is as follows. First of all, I will review the classical nucleation theory, and then I will explain the seeding method and mean lifetime method that I have used to calculate the nucleation rate. And then I will sum up my talk with conclusion section. All of us, for most of the material, we know that the melting point and freezing point are almost equal. However, there are some material, for example, water or zinc selenide, that a hysteresis exists for between these two temperatures. For example, this figure shows the temperature dependence of potential energy for zinc selenide, and when we hit the crystal of zinc selenide, it enters to the liquid state, and by showing a jump in potential energy, this phase transition occurs. However, if we cool down the liquid, it doesn't enter to the crystalline state. However, it enters to the metastable phase called supercooling state. Supercooled liquid has two destinations at this metastable phase. One of them is crystallization and the other one is vitrification. And which destination the supercooled liquid choose totally depend on its cooling rate. If we cool supercooled liquid very rapidly, it enters to the glacial state, and it vitrifies. And if we cool down it very slowly, as a result of thermal fluctuation, some crystal nuclei can form inside the supercooled liquid and leads it towards the crystallization. One of the most famous theory for describing the kinetic of nucleation in supercooled liquid is the classical nucleation theory. According to this theory, according to this theory, I don't know why. Let me hack it. I don't know how you see the PowerPoint or no. Can you see the PowerPoint?
Please, you can to change the display, please, the screen, because this is the display setting and swipe. Okay, the first.
Okay, but I cannot see it very well. Oh my God. Okay, it doesn't matter. If you see it, I can continue my explanation. Okay. According to this theory, the formation of any crystalline cluster inside the supercooled liquid requires the surmounting of a free energy barrier. And if this free energy can be written as a sum of two terms, the volume term and the surface term. Here, the gamma is the interfacial free energy, A is the area of the critical nuclei, N is the number of atoms inside the critical nuclei, and delta mu is the difference between chemical potential of supercooled liquid and crystal. If free energy of formation of critical nuclei is plotted as a function of size of the nuclei, it shows a maximum at a point delta G star equal to N star delta mu over T. And if we estimate for a spherical cluster, the size of this critical cluster N star is related to gamma, rho S, and delta mu according to this relation. And in this theory, the probability of forming any critical nuclei, J, a steady-state nucleation rate, can be written as a product of three terms: the Zeldovich factor, the attachment rate of a particle from supercooled liquid to the crystalline nuclei, and the last term is the number density of the critical nuclei inside the supercooled liquid. And the most challenging part of the classical nucleation theory is the independent determination of gamma, D plus, and delta mu. And because the scarcity of the direct measurement of these three main parameters, the accuracy and validity of the classical nucleation theory always has been questioned. In a laboratory, only moderate moderate nucleation rate can be proved. The steady-state nucleation rate between 10 power 4 to 10 power 18 can be measured in a laboratory, and at deep supercooling here in this region, the limiting step for determining the nucleation rate is the nanometric size of the nuclei and its short lifetime. And at shallow supercooling and moderate supercooling, the limiting step for determining the steady-state nucleation rate is a long time needed for formation of these nuclei. In this situation, computer simulation can help us to overcome these difficulties. Different methods exist for simulation and for calculating the J. However, I have only used two of them. For simulation, we have selected barium sulfide because a reliable potential exists for barium sulfide, which was proposed by my supervisor, Professor Hino. And also this substance spontaneously crystallizes during the cooling path of its supercooled liquid. At sufficiently deep supercooling, we can see that barium sulfide spontaneously crystallizes. So we can use the mean lifetime method to determine or to obtain the nucleation rate directly from the simulation. And also the melting curve of barium sulfide shows a large hystericity with a wide supercooled region. And in this situation, we can employ the seeding method techniques to calculate the nucleation rate. And also we can finally we can compare the nucleation drive from the seeding method with values found directly using the mean lifetime method. So this material is a good material for performing both of these two methods and compare the result. To calculate the nucleation rate using the seeding method, first of all, I have prepared a amorphous matrix containing a crystalline nuclei. To do this, I started from a crystal of barium sulfide. I want to show you the video. I start from the crystal of barium sulfide. I heated it up to 1500 Kelvin. Then at the geometrical center of the crystal, I have defined a spherical region. Then I keep the atom inside the spherical region, kept fixed at their position, and then the atom outside the seed were heated until they liquefy. And again, by cooling the liquid around the seed, we made a supercooled liquid around the seed. During the cooling of a liquid around the seed, we released it at different temperature to find the coexistent temperature. And in order to know that if the seed grows or dissolves at different temperature, we plotted the potential energy as a function of temperature. If potential energy by passing time at that specific temperature be constant or increases, it means that the seed dissolves. But if the potential energy decreases, it means that the seed is growing. After finding the coexistent temperature, we allowed the matrix plus C to evolve for half nanosecond. And during this time interval, we counted the solid-like particles in the seed environment by calculating the Sternhardt bond order parameter. And then from this number of solid-like atoms inside the nuclei, by plotting it as a function of time, we calculated the attachment rate. And then by using this formula, I have calculated the difference in chemical potential, and then substituting all of these parameters into the classical nucleation theory equation for nucleation rate, I have calculated the G for 4 different seed sizes. And then by knowing this data, I have extrapolated this data to the deep supercoolings to predict the nucleation rate at deep supercooling. For obtaining the nucleation rate using this mean lifetime method directly from the excuse me, let me escape this slide because I think I don't have much time. After implying the seeding method, I have obtained the nucleation rate directly from the mean lifetime method. For this method, I have simulated the barium sulfide at this 3 temperature because barium sulfide shows a spontaneous nucleation at this 3 temperature. And then by counting the solid-like atoms, I have determined the onset time tau, that when the number of solid-like atoms start to grow, and by substituting this time and the volume of the simulation box, we obtain J directly from simulation. And knowing the J, T, lambda, dt, and delta mu, one can find the gamma interfacial free energy, and from gamma, the size of the critical nuclei can be estimated. In this figure, you can see the number of particles inside the seed as a function of temperature, the work of formation of the critical nuclei as a function of temperature, and also the interfacial free energy gamma as a function of temperature. In all these 3 figures, The circles, the black circles, are those data we have obtained from seeding nucleation, from implying the seeded techniques. The red dashed lines in these three figures shows the temperature dependence and what we have extrapolated from the black circles to the deep supercoolings where the spontaneous nucleation occurs, and the green circle shows the data we have obtained from mean lifetime method. These three figures shows that how seeded technique is successful to predict the data at this region, at spontaneous, at deep supercooling, where the finding the nucleation rate is very difficult. And this figure shows the nucleation rate as a function of rate temperature. Here also the blue line shows the extrapolation of the black circles to the deep supercoolings. Again, it very well described the nucleation rate obtained directly from simulation. And all of this results shows that the seeded nucleation technique is a good technique to use for predicting the nucleation rate at deep supercoolings, not only for barium sulfide, but also for water, zinc selenide, and Lennard-Jones. This technique was very successful. In this figure, the circle squares shows the data obtained from seeded nucleation technique, and the circles are the data obtained from directly from mean lifetime method, and the dashed line are extrapolation of seeded data to the deep supercooling. And a good agreement exists between what seeded nucleation predicts and what simulation gives us directly. As a conclusion, I have explained how to determine nucleation, critical nucleus size, transport coefficient, the interfacial free energy by employing both seeded approach as shallow supercooling and mean lifetime method at deep supercooling. Then I showed you how seeded nucleation was successful by predicting the nucleation rate at deep supercooling, and also the results are corroborate recent findings of water model, Lennard-Jones, and zinc selenide. Thank you for your attention. Sorry if there was any problem during my presentation.
Okay, Leila, thank you very much for your presentation. We have a question here from our student Felipe. He is asking if the research is considering the crystal structure and eventual preferential growth that may occur during the process.
Sorry, can you repeat the, I have some problems with my Zoom, I don't know why, but if you can repeat, I will.
Yes, the question is that if in this research you are considering the crystal structure of your material.
Yes, the crystal structure. The crystal structure is the same as the crystal structure of the seed, if you mean. The seed has the same crystal structure as the parent material. For example, for barium sulfide, we choose the seed with the same crystal structure as the barium sulfide in crystalline state.
Okay, and you also consider some eventual growths of this material, if it is a nucleation or also a crystal growth.
No, so nucleation.
Only nucleation.
Yes, and so nucleation. And the growth is a second part of my project that I'm working on it now to study about the growth of nuclei.
Okay, and one more question is that using this simulation, are you using any experimental data?
For barium sulfide, we don't have any experimental data, but because of that, we choose two different techniques for determining the nucleation rate. One of them was seeding technique, and another one is mean lifetime method. And in this condition, we can test and examine that are those nucleation rates that we have obtained at shallow supercooling can predict the nucleation rate at deep supercooling, and to do if it is correct or not, we use another techniques, the mean lifetime techniques. And then I have compared the result of these two techniques to show the applicability of the seeding method. We don't have any experimental data.
Okay, Leila, thank you very much for your presentation.
You're
And
welcome.
here we will pass to the next